Hey everybody, this is an intro to the Quantopian lecture series. It's mainly intended for people who are less familiar, so if you're familiar with Quantopian and the lecture series, feel free to skip ahead. Quantopian is a crowdsourced investment firm. Our goal is to democratize quantitative finance and level Wall Street's playing field, and do that by providing lots of free tools and data of the same quality that you would get if you were working as a professional on Wall Street. Our business model is to provide capital allocations to the best algorithms that have been developed on the platform. Towards this end, we've developed a lot of educational materials because we want users on the platform to be well educated. The Quantopian lectures have been developed in collaboration with and are used for teaching by many professors at top universities around the world. We also work with industry practitioners to make sure everything is applicable and keeps up with whatever people are working on at the moment. In general, we try to teach theory and intuition through hands-on applications so that you have the code ready to go once you've learned a concept. So without further ado, let's see what's on deck today. Today we're going to be covering p-hacking and multiple comparisons bias. P-hacking is really just abuse of multiple comparisons bias to an extent. They're, same sides or different sides of the same coin. And we're going to go ahead and get to that lecture here, which is right here, lecture 16 right now, although those numbers change as we add new lectures in and sometimes move them around. And as always, we're going to check out the notebook and dive right in. So p-hacking is a really huge problem in basically all of statistics and data science. And it's become especially bad recently because not only do we have statistical frameworks built up, but recently we've started developing techniques surrounding big data and machine learning and artificial intelligence. And all of these fields are fields in which you run many tests in some way or another, right? You're trying tons of different models and seeing if they work. You're making tons of different decisions. And at the end of the day, you're going to have a lot of false positives as a result of that. And we're going to kind of talk about why today and explain it and really kind of, explain why this is an issue and some of the ways that you can handle it. And at the end of the day, I think something that's important to notice is that this issue is not just related to statistics, right? Like we all make decisions all the time. And at its core, multiple comparisons bias is really just saying that if you try a lot of stuff, some of the stuff is just going to, look good by random chance. Or if you try a ton of times, one of the times you're bound to get lucky. That's really what multiple comparisons bias is. And so whereas statistics provides a rigorous framework for you to think about this issue and deal with it, it actually applies to your everyday life. If you're making decisions on a day-to-day basis and you're making tons of different decisions, well, you probably want to at least have a sense of maybe, did I just get lucky here? Is this actually meaningful? And statistics provides us tools to think about that. So as always, the first thing we're going to do, import libraries, because we need libraries. And as a quick refresher, there's a whole lecture on Spearman rank correlation earlier in the lecture series. But what you have to know about Spearman rank correlation is that it's basically a correlation that's a little bit more robust to weirdness in the distributions of your data and outliers. And the way it does that is it just ranks the data, and then it takes the correlation of the ranks rather than the raw data. So you can imagine, if you have some data point which is just way outside of normal bounds and outlier, rather than that data point actually being like way outside of normal bounds, it'll just be a rank, so it'll be the top ranked data point, but it's only one rank higher than the next one. So it's a way of normalizing stuff down into a much more well-defined scale and seeing if there's actually a relationship. Now that said, of course, you lose information. It could be that outlier was actually meaningful, but it tends to be a bit more robust, at least for some problems. And we do a full, array of experiments in the lecture on Spearman rank correlation just to check how robust it is. So you can actually go and check it out. The test returns a correlation coefficient, which is the same, can be interpreted the same as a regular Pearson's correlation coefficient. And When you do a correlation normally, the default correlation statistic that's returned is what's known as a Pearson's correlation. That's just the kind of the accepted default for correlation. And so Spearman rank correlation coefficient is just the same statistic but computed differently, right? It's computed on the ranks. And you interpret it the same way. Coefficient of 1 means that there's a very strong perfect relationship that causes, covariance, one to move with the other. -1 means they move in opposite directions, but they're still very, very, perfectly related. And then as soon as you start having any kind of real noise in your data set, when they don't move together all the time, the coefficient will start dropping. And when it reaches 0, that's when you say that there's just no relationship whatsoever. It's completely random. They just kind of move around and they're not, there's no evidence of any relationship. So here, just as a test of that, we'll generate a random time series here, x, and then we will make y equal to x, and then we'll just take the Spearman rank correlation of y and x and get the coefficient out of the results and get the p-value out of the results. And you can see here that the Spearman rank coefficient is 1 and the p-value is 0. Now, notice that we didn't set a cutoff before computing that p-value, and we'll go into that in a second of why that's important to do. But the next thing we'll check here is just that you see x is, again, just a random time series, and now we're going to make y depend on x, but we're going to put in some noise, so it's not perfect anymore, just some more randomness. And you can see the coefficient decays. An important point, again, as I said, is you really need to choose a cutoff before interpreting a p-value. P-values should really be interpreted as binary. You can look this up, but basically you shouldn't interpret a p-value as a probability. That's really a classic mistake. P-values are just measures of whether or not your null hypothesis should be rejected. And in this case, what we're saying is our null hypothesis is that there's no relationship, and then we have to choose a significance level. Right? And our significance level in this case, let's say we chose 5%. Well, in this case, this p-value would be below 5%. So we would say at a 5% significance level, we choose to reject the null hypothesis that there's no relationship and accept the hypothesis that there is a relationship. And you have to be very careful when interpreting p-values because it's very easy to start reading them as probabilities, and that's actually very wrong, and you'll end up with a lot of problems if you do that. But there's a full lecture on it, and you can go and check that out. And in general, if you treat p-values as non-binary, what it allows you to do is kind of retrospectively say, oh, this p-value is really good, right? This is so low, so this must be super significant. But in reality, p-values are just kind of uniformly distributed. In the presence of of a random signal, they should be uniformly distributed. So it's not correct to think that something being lower means it's more significant. It's only significant if it passes under that cutoff that you defined earlier. And if you don't follow these steps carefully, well, you're basically just kind of like, freestyling it, and you've lost all of this framework that, statistics has built up for you. So just be very careful when interpreting p-values. And we have, a lot of lectures that kind of deal with this, but this one in particular is a good one. Here, I'm just going to run this experiment again, just so that we can, see the result again. And you'll see we get a slightly different coefficient each time because it's random noise. But actually, let's increase the amount of noise. So we'll multiply by 3. And you'll see much lower coefficient, 4, way lower, 10, even lower. So, as you're adding more noise, the coefficient's going to drop. So again, please, 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 when you're interpreting p-values, have a cutoff chosen in advance. You need to choose the cutoff before you've seen the p-value. Otherwise, it's not meaningful. A default is often 5%. But keep in mind that if you have a 5% cutoff, right, that means that it's a 5% significance level, which means that there's a 5% chance that you get what's known as a false positive. So again, to explain this, you can kind of think of in the following way. So there either is a relationship in your data or there isn't a relationship in your data. That's what you're testing for. And if there is a relationship in your data, then that's what's known as a positive, a true relationship. And if there isn't, that's known as a negative. So if your p-value falls below your cutoff and there is a relationship, that's known as a true positive because you have found it and it's a true relationship. So it's a true positive. If your p-value falls above in that case, that's known as a false negative. It's a little tricky because you kind of have to draw it out on a piece of paper. I strongly recommend drawing it out on a piece of paper. It'll be a lot clearer. But that's known as a false negative because it's a negative result, but that's false because the actual result should have been true. Likewise, if there's no relationship in your data and your p-value falls below your cutoff, that's known as a false positive because you got a positive result, but it was false. And similarly, the vice versa applies. So in general, what we're worried about is false positives here because a false positive gives us evidence and starts us thinking that there's a relationship when there actually isn't one. So that's kind of the danger case, especially in quant finance, that we want to avoid. Now, if you have a significance cutoff of 5%, what that means is that if there's no signal whatsoever in your data, there's still a 5% chance that a uniformly distributed p-value falls below your cutoff. And that's the definition of the cutoff. It just says, if your test is correctly calibrated, right? All tests have assumptions underlying them, so make sure you've checked the assumptions of your tests. I always say, make sure that you actually look up all the assumptions underlying a linear regression before you run a linear regression because there's a good number of assumptions and, a lot of people don't check for them. But if your test is correctly calibrated and there's no signal, then it should just be uniformly distributed and you're saying, well, I pick a 5% cutoff for my p-values because that means that there's only a 5% chance that I'll get a random p-value that's, underneath this cutoff in a false positive. So it's basically saying that in the presence of no signal, there should be a 5% false positive rate. And you can adjust that, right? It doesn't have to be 5%. It can be 1%. It can be 10%. It really depends on what you're trying to test for and what you want your false positive tolerance to be. And, in something like a fire alarm, maybe it's okay to have that a little higher because there really isn't that much of a negative consequence of a fire alarm going off. But in, a military installation that's supposed to be detecting inbound missiles, you might want it to be a little bit lower because on the one hand, if a missile hits the States, that's really bad. But on the other hand, you don't want to start a war because a flock of pigeons flew past your radar station, right? So in practice, it's all about what you're actually testing for and what you want your false positive rate to be. And we'll just do a little experiment here, which is, we'll say, okay, well, let's set our cutoff to be 5%. And then we'll just do our experiment again. And we'll just check if the p-value is below the cutoff. We won't even look at the p-value. This is really the right way you should do it. And in this case, we say we're going to reject our null hypothesis. There is significant evidence of a relationship in our data, okay? And keep in mind that at no point we've said anything about the probability of a relationship existing. It's complicated and it gets into really weird stuff when you try to figure out in frequentist statistics what it means to say that there's a probability of a relationship existing. Really all you're saying is that given a 5% rate of false positives, this thing, passed my test, and so I'm going to accept it knowing that there's a 5% chance that I could be wrong is kind of one of the ways to interpret it. But you have to be very careful, and I make mistakes all the time when interpreting it, so I tend to just actually have to go and read it every time. And you know what? Given the number of statements I'm making in this lecture, I suspect that I will also make a mistake at some point in this lecture just because I'm saying so many different things. So if I do, please email me and tell me so I can fix it. But also it's just should be a lesson to, don't trust anything I say implicitly. Really, cross-check and look it up before you try to do anything fancy about, interpreting results. However, let's move on to the next phase here, which is we're going to try running a bunch of tests and seeing how that works. So the first thing we're going to do when we're running many tests is we're going to define a data frame, and then we're going to add n randomly generated time series of length t. So we're just saying, make a time series of length 100 and do that 20 times. Super simple. That's what this looks like. We're just looking at the first 5 time points for each of our 20 in this data set, x0 through x19, indexed from 0. And you'll notice just completely random values. There's no signal in this data set, none whatsoever. They are not related to each other at all. So we've constructed effectively a benchmark. This is a no signal data set, and now we're going to start running tests on it. So the first thing we're going to do is we're going to write this little function, and we're just going to say our significance level in this case is 5%. We're going to keep a list of any pairs that we found that were significant. And we're going to say for, each pair, so we're just going to loop twice so we catch all the different pairs here. And we're just going to say, here's the first time series, here's the second time series, do Spearman rank correlation on them, and then say, is this Spearman rank correlation p-value less than our 5% cutoff? If so, append to your results. So this is very, you can imagine if you're running on this like big data database and you're looking at 100,000 different entries and you're running a test on each of them, it's a similar situation. You're kind of looping and doing many tests. But of course, in our case, the number of tests that we're doing is going to be this. This is just the math formula for how many pairs you have. If you have n things, all the possible pairwise relationships. It's kind of a introductory combinatorics thing you might learn in a discrete math class. If you haven't seen this before, take my word for it and go look it up. There's actually some cool reasoning behind why this is true. It's also known as the handshake formula because it counts the number of handshakes that have to occur in a crowd for everybody to handshake everybody else and a crowd of n people. And so it's all completely random, remember, in our data set. But we're going to run this code on our data set and see how many things pop out. So mathematically, we should expect, if we have a 5% cutoff, that means that if our p-values are coming back uniformly distributed, then that means that we should have this many tests that are run, and 5% of them should come back as false positives, just as our background rate. And so we should expect 9.5 false positive p-values. When we're running this on real data, we don't know that they're false positives, right? We don't know that there's no signal in the data. So what we'd see is we'd expect 9.5 positives, right? Period. It's kind of like we don't know if they're false or not. And that's why it's tricky. And so let's actually see what we got. And what we got was 14. Okay, well, that's not quite 9.5. It's actually more, right? Which is a little worrying. But let's go ahead and try running through this whole experiment again and see what we get. 8. Okay, that's closer. Let's try it again. 7. Okay. It's in the neighborhood. Let's just go ahead and run it a lot of times and see what happens. So here we do the experiment. We make a little function to do that experiment we just did, so I don't have to rerun it every time. We're literally just going to do it 100 times, save all the results, and then count the number of times that we saw a significant p-value, and then take the mean. Right? So, we're just going to do what we just did before, but just take the mean many times over this number. And you can see here in this simulation when we did it, you got 9.3, which is very close to the 9.5 that we would expect. And the more you increased your number of experiments, the more you would see this converge, right? This is just, the bigger numbers means things converge more. So I'll run it again. It might take a little, a few minutes because it's running a lot of stuff in here. But you'll see, this is going to be a much more consistent number. And really what this is just saying is that in any given experiment of doing this, you should expect about 9.5, between 9 and 10 false positives. So just to visualize what's going on here, p-values, again, should be uniformly distributed if there's no information in the data. There's no relationship in the data, so there should be no information that's carried over to the p-values. So they should be uniformly distributed. And it's equally likely that you would get 1% p-value of 0.01 as you would get a p-value of 0.99. It's just no difference. And so here what we can see is that if we define another function to actually pull out all the p-values from the experiment and plot a little histogram of those looking at how they're distributed, well, if we run this experiment on n time series of length 100, 10 time series of length 100, this is what we see. And it's pretty noisy. And again, it's just we haven't started converging yet. So what we need to do is we need to up the number of time series so we do more comparisons and get more p-values. So if we change this, and I'll just rerun this experiment again, so you can see you'll get another noisy histogram. So if we changed this to maybe 20 and reran it, you see, okay, starting to look a little flatter. 30, Okay, flatter. I have one that I put in the oven earlier here, which you can see is 50. That's even flatter. So really what this is doing, again, it's converging to that uniform distribution of p-values. No one is more likely than the other. And what we can do here is we can just plot some artificial lines. And what this shows is it just visualizes where these cutoffs are. So what we're saying with a 5% cutoff is, well, any p-values that fall below here in a uniform distribution will be counted as significant even though there's no signal. And you can see it's harder to get below 1% cutoff. There's just less stuff that lives here. If you threw a dart at this page, you'd be less likely to get something in here, somewhat likely to get something in here. And so basically what it's saying is a lower p-value cutoff will reduce the likelihood, by definition, reduce the likelihood of false positives. However, there is a trade-off. The first thing we're going to do is we're going to use this lower cutoff now and redo the experiment, and you see we get a far lower rate of false positives because we use a lower cutoff. This is what we would have expected, so again, very close to what we expect because we're running on a large number of experiments. However, this is known as the sensitivity-specificity trade-off, right, where if you lower your p-value cutoff, it makes it harder to actually find stuff that's real because, basically it decreases the chance that you'll find a real relationship because in a real relationship, the p-values are also going to be noisy. And so it decreases the chance that you get below that cutoff that you've chosen that's lower. So the way I always think about it is if you're taking a fire alarm and you're moving it around the house and you're deciding where should it be. Imagine you put your fire alarm right above the stove, right? That would effectively be an incredibly high cutoff, right? Because it means that you just constantly have this thing be going off. So many false positives. However, the good side is that if you could tolerate all of those false positives, you would be almost certain to catch when an actual fire occurred on your stove, right? So that would be, kind of like a test that would be way too sensitive. And on the other hand, you could try to make it a lot more specific, right? Where you say, okay, now I'm going to actually take this thing and I'm going to put it in the garage, right? Like not even in the house. So at that point, you're basically never going to get a false positive from the stove going off. You might if there's your car is emitting smoke or something, but you're not going to get a false positive from the stove going off. However, you're also not going to catch a fire, right? Because by the time, a fire gets into the garage, it's going to burn down the rest of the house. So this is the way I like to think of what cutoff you should choose. And it really is just about choosing a cutoff that makes sense for what you're doing and what your risk tolerances are for that problem. And just trying to pick one that's, gets you into a good ratio, a good room, a good area as far as how many false positives can you tolerate, how bad are false positives, and how bad are false negatives, right? Which is the flip side, which is that you don't find it, but you really needed to find it. In finance, false positives tend to be a lot worse than false negatives because if you don't find a relationship, that just means that you don't trade often, right? And so you're not at risk to lose money. However, if you find a false positive and you try to trade that thing, you are at risk to lose money if this thing turns out to be wrong and you take on, too much risk or it's actually the reverse of what you thought would happen. So in practice, in finance, I tend to weight false positives as a little worse than false negatives, actually significantly worse. And there's, caveats to that and lots of complexities and, don't take that as gospel, but just in general, that's my rule of thumb in finance. In other areas, that may not be the case. So just be aware of that trade-off. And in general, when you're trying to reduce multiple comparisons bias, so how do you deal with this? Well, keep in mind that you can't ever eliminate it. You can really just kind of reduce the risk that you do have to multiple comparisons bias. And the first option is just run fewer tests. Don't run as many tests. Don't take a neural network that's going to implicitly run a ton of tests under the hood. And keep in mind that you don't have to actually like sit there and type out the code and run a p-value. It's literally any time that something is making a decision about whether something's significant, right? That's what's going to expose you to multiple comparisons bias. So the more simulations you run, the more tests you run, whether they're manual or whether they're under the hood of an artificial intelligence or machine learning algorithm, they do count towards your multiple comparisons bias exposure. And so oftentimes one of the best ways is just to run fewer tests. And one way that a lot of people deal with this is they try to come up with hypotheses based on, their expert knowledge of the system, rather than doing this what's known as data mining, which is actually when you basically, that's another word for multiple comparisons bias. It's known as data mining. And some people have actually kind of co-opted that term and taken it to mean something good, which is like searching through data for interesting signals. But it's one of those mixed terms. I tend to use it to mean something bad, which is like just, mining through your data until you find something, whether or not that thing is good. So in general, you kind of try to avoid data mining and kind of come up with an idea of how the world works and then go test it and see if it fits the data, right? That's like running fewer tests rather than looking at a data set and just running a bajillion tests on it until you find something that pops out that's good. Because oftentimes that's just going to be way overfit to the data. It might have just gotten lucky. You don't know, right? It's really hard to know. And the other thing that you really need to be aware of is out-of-sample testing can do a huge amount to reduce your multiple comparisons bias, because if you split your data into different sets and you have sets that are reserved to be like unbiased out-of-sample tests, well, what that means is, you do all your analysis on your in-sample test and then you get something that you think is really good and then just go and test it once. Just do one test on the out-of-sample data and make sure it holds up. And if it holds up, that's a pretty good indication, because the out-of-sample test is not only are you doing one test on the out-of-sample data, but it's also data that you haven't seen before. So it would have been really hard to overfit your algorithm to it. We have another whole lecture on overfitting, by the way, if you want to learn more about that particular side of things. So out-of-sample testing is a really good way to try to avoid it. And one thing to keep in mind, and I always say this, is one big failure mode with out-of-sample testing is when you train your model on the in-sample data, you develop a hypothesis, you train it, you're like, that doesn't quite work, so you tweak it a bit, you train it, blah, 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 and then you get to your out-of-sample test, you run it, it doesn't work, okay, so you go back and train it, figure it out, okay, you get to your out-of-sample test, run it, it doesn't work, and do that until it works. Well, the moment that you've actually ran a test on your out-of-sample data, it's no longer true out of sample. It's now kind of it's been touched and needs to be moved into your training data set. And there are, some exceptions that you can make to this if you really know what you're doing, but in general, just assume that it's touched, you can't deal with it anymore. It's now training data. You need to have more new data that you haven't seen before to be out of sample data. So that's why I always recommend, actually, if you have enough data, splitting it into, training sets and then multiple out of sample testing steps, because, you're never going to get it right the first try. And also just reduce your risk of overfitting and multiple comparisons bias by having good behavior on your training data set, because, you can think of it, you're wasting your out of sample data tests, which you only have very few of, if you just overfit a ton or run a ton of tests and then, do an out-of-sample test and it fails. The other option is using what's known as like an adjustment factor or correction factor. One of the common ones, and probably the most common, was what's known as a Bonferroni correction, and it's the most conservative one. So what that means is you're basically going to take the significance level and you're going to say, okay, well, if I want a true 5% significance level, the significance level that I actually compare my p-values to needs to be different depending on how many tests I'm doing. And the idea is very simple. It's just that if you run m tests and you want a significance level of a, you should expect m times a false positives, right? So you have to divide your significance level by m so that it cancels out in the wash, and what you'll see is, you expect MA false positives, but you've divided your significance level by M, so you should expect M, like a ratio of M fewer, so you should expect A false positives, because the M's cancel out. So it's a way of getting yourself back to A. It's a little tricky to think about, but let's actually go through the experiment. It might be clearer. Basically, all you do is you say, okay, our desired level is 5%, and we're going to run this many tests. So we say our new cutoff level is just our desired level over the number of tests that we're running. This is known as the Bonferroni correction step here, and this is your kind of Bonferroni corrected significance level. And you're going to do your experiments again, but this time you're going to use the new cutoff as your experiment. And you'll notice that as a result, we get far fewer false positives, which makes sense because we wanted it to be a very low number in the first place. We want it to be 5%, and this thing it's not going to be consistent every time, but you'll notice that it will kind of do a decent amount in reducing the number of false positives you get, just because it's very kind of ham-handedly reducing the cutoff. It's providing a synthetic, like, kind of false cutoff that it's being compared against, and then that will kind of work out in the wash to the actual cutoff you wanted over all the different tests. If that doesn't make sense, I recommend just kind of like reading more about it online, actually working with it, trying it, seeing what happens, and getting your hands a little dirty. But I think it should be a fairly intuitive concept when you get your head around it. Bonferroni corrections can be overly conservative and make it very difficult to actually detect anything. As an example of that, let's say that there's 100,000 possible relationships you want to test. Well, at this point in time, what you're saying is like, there's a very low chance of getting a false positive with a Bonferroni correction because you'd have such a tiny, tiny, tiny p-value cutoff. But also, it would make it a very, very, very difficult for a true relationship to pass through your significance cutoff. So again, you get back to that sensitivity specificity problem where a Bonferroni correction, it kind of moves the fire alarm into the garage for you and makes it very difficult to detect true relationships in your data. P-hacking, to actually define this term, is just the kind of abuse, either intentional or unintentional, of multiple comparisons bias. And it's incredibly common. It's incredibly common in scientific literature and peer-reviewed publications, in all sorts of different stuff. I mean, you see tons of people will talk about like, oh, I was successful in business because I did this, right? But you don't see all of the people that failed. And so like that's known as survivorship bias, but you can also think of it as, well, you kind of ran a ton of tests and one got lucky, and why are you trusting this one so much, given that you ran so many tests? And, so it's incredibly common in life, in academic literature. And if you think about it, if a research lab tries 50 different experiments and then a couple work, and then they take those ones and publish them, and then a bunch of other research labs all try 50 different experiments, like the number of tests being performed every day in academia is very high. And so that's oftentimes why in academia, instead of trusting any one paper, there generally tends to be an effort to try to build consensus, to reproduce results, which is really kind of an out-of-sample test to reproduce results, and wait for a few different papers to come out that confirm the same effect. Because of this p-hacking, and it's hard, oftentimes academics try not to do it, but they unintentionally do it, and sometimes they intentionally do it. It's hard to know from any one result if something is really good and real, and that's why out-of-sample testing is so important. And in general, like I said, to repeat, you can never eliminate this type of stuff. You can only reduce it. And, in general, just be intelligent about trying to reduce it and really do use out-of-sample testing. That's all I had for today. Here's some more sources, but please go through this lecture. It's really important. I think it's crucial for understanding statistical analysis or any type of research, especially in this new age of big data and data science and machine learning and artificial intelligence. Please go through it, understand it, and run the experiments and get your hands dirty, and then go back and think how you can start applying it to your own analysis. Hey everybody, thanks for watching another Quantopian lecture video. I just wanted to say that all the lectures are always freely available at quantopian.com/lectures. We also hold workshops around the world. Information on those can be found at quantopian.com/workshops. We work with local experts to bring you full-day interactive hands-on approaches to learning this stuff and try to focus more on giving you the tools so that you can leave the workshop able to learn more on your own than trying to cover any specific technique. For information on events near you, you can check our events page, also linked from here, and see if there are events coming up nearby that you might be interested in. This also includes meetups and hackathons and all sorts of stuff in addition that we do to try to make education more accessible. Lastly, if there's anything that confused you today, or if you want to start a discussion on the stuff that you learned, please head over to the community forums available under Community Forums in the menu bar. Post a question, look for other similar questions. In general, it's there to really give you more tools to keep moving forward and not get stuck and continue using the knowledge that you learned in the lecture series. So again, thanks for listening, and hopefully I'll see you again soon.